This video is an overview of proofs, and while proofs are generally thought of in a math setting, I want to show why I believe it can apply to the real world as well. So what is a proof? A proof is just a guarantee that a statement is true or false. So if you've proven something to be true, it's guaranteed to be true. And by statement, I mean something where you have some kind of condition, and anything that matches the condition is follows some pattern or rule or something else matches some other condition. So as an example, if you have an odd number and an even number and add them together, you get an odd number. That would be a statement, and then if we prove it to be true, then we know that's guaranteed. So we're saying for every single possible combination of an odd number and an even number, when you add them together, you get an odd number. And another example statement would be for every action, there's an equal and opposite reaction. So again, we're saying every single possible action, something else is true. And it's worth noting that there's the opposite side of the statement as well, where you can have not all or at least one. So I could say for at least one combination of an odd number and an even number, you add them together and get an even number. But in the context of this video, I'm only going to be considering statements from the all or nothing side, but the opposite side is also a statement as well, the not all or at least one. So in the math world, there's a lot of different techniques to proving something to be true, and I'll just go over some big points. Proving something false is generally easy in the sense that all you have to do is show that there's a single counterexample, and then because that counterexample exists, then you know that the statement is false. And a counterexample is just showing that there's one case where the statement you said isn't actually true. And sometimes it can be really difficult to find a counterexample, so it can be hard in that way, but once you've found it, you don't have to do any work to actually prove something is true. You just say the counterexample exists. But on the other hand, if you wanted to prove something true, it's hard to do because you have to show that it's true for every single possible input. And a lot of times there's so many possible inputs that it's either infeasible to go through every possible one, or they're actually infinite, so there's no way you could ever go through every possible one. And so you generally don't want to try and prove anything by showing a bunch of examples of it being true, because that doesn't, you can't cover every possible input that way. So if the space is finite, you could test every single possible input, but again, a lot of times the spaces are so large that even if you could do it, it's impractical, and so you wouldn't want to prove something that way. So how would you actually prove something? Well, one thing you could do is you could use a pattern or a rule that covers every single possibility. And in the math world, because we designed the system, we created the rules and the definitions that govern everything, we have the rules and the patterns that cover every possibility. So, for example, we define an even number to be a number that's 2 times an integer, and an odd number is a number that's 2 times an integer plus 1. So we now have a rule that covers every single possible even number and every single possible odd number. And then if we use that rule, we can say when you add them together, you get 2 times something that adds up to be an integer plus 1. And that's, by our definition, an odd number. So now we've proven for every single possible even number and every single possible odd number using this rule, we get something that's an odd number using the same rule. So because we used a rule that covers every single possibility, we no longer have to manually test every single possibility, which you, again, couldn't do anyway because it's an infinite space. We just say we've we've shown that it's true for every single possibility because we have a rule that covers it. So that's how things work in the math world. But what about the real world? Again, you generally can't test every single possible input if you have a broad theory. But in the real world, you can't use a rule that applies to every input either, because in the real world, we didn't create the rules that govern the system, so we don't know what they are. We can try and make guesses, but we can't prove our guess because there's no rule that covers every single possible case. And again, you can't test every single possible case. So you can't prove your general theories true. And that's because you would have to test an infinite number of points, what you can't do. So if that's the case, then you might think that you can't really use math logic in the real world, but I don't think that's true. So now I'm going to talk about some ways where I think math logic still applies even though you generally can't prove things true. So even though you can't prove something to be true, you can use your math logic and reasoning to try and figure out what you should test and what your level of confidence should be. So a lot of times people will have a really high level of confidence if you show a lot of examples of something being true, but that's wrong, just as it is in the math world, where you can't prove something true by showing a lot of examples of it holding true. If there's just one single counterexample that shows that it's false, then it's actually false. So that right there should help guide your level of confidence. So even if you have a lot of examples of something being true, if there's still ways where it could be false, then you have to still have some doubt there because it still could be false. So because it's so easy to disprove something, then you have to keep that in mind and say, okay, there's a lot of ways it could be proven false, so I can't just believe it to be guaranteed true yet. So then for what to test, you have to analyze from the different ways that something could be wrong. So maybe you're making a theory about people, and one way your theory could be wrong is because the ways things behave differ based on the person, the individual. So it might be different for different people. So you would have to test that. You would have to analyze that. And if you can show that it's probably not wrong in that way, well, you've now increased your confidence in the idea. But you would have to think about the other ways as well that it might be wrong. And then at one extreme, well, maybe the universe isn't real and we're just feeling simulated sensations. And that's always a possibility. But if you have to go that far out to think of how something could be wrong, well, at that point you can be pretty comfortable in assuming that it's true. But there's a whole bunch of different levels in between before you reach that. So as long as there's a lot of different ways that something could be wrong, you have to have that doubt there, and you want to analyze those different ways that it could be wrong. And once you can show that's probably not wrong in those ways, you can increase your confidence in the idea. Now, there are some well-defined systems in the real world. I think coding is a good example where we create the rules of how code works. So as long as the hardware functions correctly, then we know the rules that govern how code works. So we can actually prove certain things to be true. And I think math logic is really useful in coding, especially like debugging something, because if you can show, okay, this part is guaranteed to be correct or guaranteed to be wrong, if you understand what you need to do to show that, then it can really help you pinpoint like exactly what you need to test and exactly what you should look at, and then you can fix problems a lot faster. So having good math logic actually helps with coding, I would say, because it would mean that you have a good understanding of like what's guaranteed to work, what's guaranteed not to work, and all of that. Games as well are well-defined systems. So you can make proofs about things in games because, again, we created the rules that govern the game, so we know how it works. And there are some exceptions where, like, even if you create the rules, sometimes they're so complex, like some of the interactions in complex games are so complex that you don't necessarily know how it all works. Like maybe you're talking about a racing game where if you collide with a wall or something, technically we've coded how that should work, but maybe the interactions are too complex, and the best we can do is analyze how it works by from observations, and then at that point we can't actually prove theories about that because we have to use observations and we can't observe every single point. But as long as we do have all the rules and they're well defined, then we can prove things about the game. And then another example would be theories themselves. So we can't prove our general theories to be true, but if they just seem to be true and we're fine if we're fine assuming that they're true, then we now have a general rule that we can use to prove other things that would also be true. But as always, it's important to remember we can't prove the base theories, so we don't want to go too crazy with just assuming that it's always true and go too far um, into proving other things unless we feel really confident that our base theories are correct. And that is something that I think is also important to really understand. So, if you really understand that most things you just can't prove them true, then it naturally leads to you being more open-minded because you understand, well, we can't prove it to be true. There's a lot of different ways it could still be false. So, there's always the absurd cases like the universe not being real or whatever that can make your theory to be false, but not all theories require absurd cases like that to be potentially false. There's again a whole bunch of different levels in there, and a lot of times people will only look at the positive points that support their theory, and as long as there's a bunch of those, they'll believe that their theory just has to be correct. But as long as there's still ways for it to be wrong, then it still might be wrong, and you should stay open minded and not close out other possibilities. And it's a difficult concept, but you'll see people get it way wrong a lot of times when they use the word proof casually. Like they'll say something is proven to be true, or um, something that where it's like if you ever hear people say something has been proven true multiple times, they they generally don't really understand what proven means, or they're just using it very casually and not technically correct because um, if what they generally mean is that you've seen multiple examples of it being correct, but that's not a proof, and that's a very poor way of thinking of proofs because again, you can never prove something true with a bunch of positive examples unless you can test everything. And for most things, you can't test everything, so you have to prove something in a different way. So, um, so it's important to really understand what you have to do to prove something to be true, so that you don't just assume that something is true even when it has a lot of plausible ways to be false still. And then the opposite is also there, where if you can actually prove something to be true, then you can be closed minded because it's guaranteed to be true. So sometimes people won't understand that something is actually proven true, and they'll try and argue that it's um, it's still debatable or something like that. But if you can actually prove something to be true, then it's guaranteed. But the more common case is that people assume something is proven true, so they'll just say the word proven too often, and it'll be something that's not at all proven true. So they'll think of something as guaranteed when it's not. But there is the other case of something actually being guaranteed, and people will still question it. So I do have some notes, but one big thing to remember is that something being unproven does not mean that it's false, and that doesn't even mean that it's more likely to be false. That doesn't even mean that you're saying you don't think it's true. If you say that something is unproven, you're just saying that's not guaranteed to be true. But if you aren't able to prove that it's false either, then it's just unknown. So it's not guaranteed to be false either. So if you can't prove something true, you should stay open to the other possibilities. But just because you haven't proven something to be true doesn't mean that it's necessarily even not likely to be true. It's just not guaranteed. It's just not 100%. It could still be 99.9% likely. It's just not 100. And then another big point is that false doesn't mean bad. So a lot of people have this instant association where if you say something is false, well, that must mean that it's bad. And that's really not the case. So you can have something that's false, like proven false, can still be very useful in a lot of different ways. And it could be a close approximation of something. So it's proven wrong, but it's close enough and maybe simple so that it's still really useful. Or it could be true under certain conditions, so it's proven wrong in certain cases, but maybe in other cases it's actually true. So now you just have a better idea. Okay, for these cases, I can use this idea. For these other cases, I'm missing something or I need to figure something else out. So even if it's not useful in those ways, if you show that something is false, that is going to show you different things that you need to consider better or different things that you didn't take into account. So if you use good reasoning, then you can find different points that need to be tested to create another idea that's better. Or you can have a good understanding of what your first idea was missing. So you can come up with an idea that's false, but you can, even though it's false, you can use it to progress towards an even better idea. Then, to close everything out, I think math logic can apply to the real world, and even though the real world runs on a system of rules that we didn't create, so we can't prove things in the real world, if we have the right mentality, we can find the right tests and have the right level of confidence in the things we believe. So it's really easy to get that wrong, where we think something just has to be guaranteed, even though it's very far from that, or we question something that is actually guaranteed. And then if we have a system that we did create and is well defined, then we can use this type of math logic on it and actually make proofs. But proofs are really hard. This is really just the rough overview of it. It's not going into any of the depth, and there's a lot more to it. And I hope to cover a lot of that in other videos, but it gets pretty complicated pretty quickly. So this is not some easy thing where you can just like watch one video and then all of a sudden know how to prove everything. It's a complicated subject.